This part of the course is about a Python library for doing fast operations on arrays of numbers called NumPy. This may seem like a pointlessly over-specialized thing to do, so I just want to talk through why it's important. First, let me give an example of what it's like to use in practice. Suppose I have two lists, x and y, and I want to add them element-wise to create a new list z. Here's the straightforward way to do it, and any programming language at all will let you do something like this. We'll use a for loop. This syntax says let I go from 0 to 3, and we add together the ith element of each of the two lists x and y, and we append the answer to the z list. Very straightforward. Here's the NumPy way to write it. Let x and y be NumPy arrays. They have just the same elements, but we've told the computer that these are NumPy arrays, not Python lists. Then, to add them element-wise, we write z equals x plus y. So what's the big deal? There are two things. First is conciseness. The NumPy syntax is closer to maths, and if you're doing mathematically oriented work, which scientific computing is all about, then that's very handy. It means your code is more concise, which means less time between having an idea in your head and running it in the notebook. And it's easier to debug if what's in your editor matches what's on your blackboard. The second reason is about efficiency. If we're training a neural network, for example, we end up doing an awful lot of these matrix operations. And for speed, the matrix operations are farmed out to multiple cores or to GPUs on graphics cards. So the way the addition actually happens may be nothing like the simple for loop. We may have chunks of the loop running in parallel, split across different cores, and there might be all sorts of very clever tricks going on to do with getting the right data from memory to GPUs in time to keep the GPU busy. The exact way it's optimized isn't something we want to think about. We just want to state our intention, and we want to state it as high level as we can, so that all the clever library optimizations have as much chance as possible of reorganizing the job to suit the hardware that we're running on. It's silly for us to impose a sequential ordering on this addition, as we would do with a for loop, since that just constrains what the library and the hardware might be able to do to speed it up. So that's what this section of the course is all about, learning how to use the high-level NumPy library to state what it is that you want computed. You've got to get used to steering clear of Python for loops, and you've got to get familiar enough with NumPy alternatives. It's basically putting yourself in a straitjacket, but at least you do get the sweetener of more concise maths-like code. Now, something about all of this feels a bit like the child's game Simon Says. Do you know the game? The teacher calls out, "Simon says, clap your hands," and you clap your hands. Then the teacher calls out, "Simon says, put your hands on your head," and you put your hands on your head. And the teacher calls out, "Touch your nose," and if you touch your nose, then you're out, because the rule is you only do what Simon says. And that's what NumPy coding feels like. You don't do a sum, you do a numpy.sum. You don't do a exponentiation, you do numpy.exp, and so on. All I can say is it's worth it, because all the nice juicy libraries for training neural networks are all patterned exactly after NumPy arrays, and they all have this Simon Says characteristic. This is just the price you have to pay for doing machine learning.